Section 3.6 is about the chain rule, which is one of the most powerful functions, one of the most powerful rules we have when it comes to understanding derivatives and performing derivatives. Now, the knowledge of the chain rule has to work with your knowledge of composite functions. So we're going to review composite functions. So we're going to start with saying that f of x is equal to 2x and g of x is equal to 3 plus x. So if I said that I wanted to find f of g of x, what that means is that I am going to take 3 plus x and I'm going to put it where this x is, right here. So let's do that. And f of x is 2, and I'm going to put 3 plus x in it, and we have 6 plus 2x, a composite function. Now with composite functions, you can substitute one function inside another one at any time. So if instead I wanted to plug f of x into g of x, I would take my f of x, which I think I said was 2x, and we're going to substitute it where x is in our g function, which was 3 plus x. So we're going to plug 2x into 3 plus x. And then that means y would be equal to 3 plus 2x. And that is our composite function. Now these are a little simplistic. What we are going to be doing with our derivatives is looking for that inside function that you can easily identify as being f of x that has been substituted inside another function. So let's say now that f of x is sine of x and that g of x is x squared. So if we were going to say that y is equal to the composite of putting g of x inside of f of x, then we would take our f of x, or g of x actually, right here. We're going to put it inside this x. Now this should be a little familiar, as in we were substituting an x plus h when we were learning to find derivatives. So if we put x squared inside of sine of x, we'll have sine of x squared. Now in this case here, we can think of x squared of being inside and of sine of x of being outside, because the sine is completely determined by what x squared is. So if we were trying to find the derivative, it's a little difficult now. We know that sine derivative is cosine, but x squared has its own derivative, and we have to take that into account when we're taking the derivative. So we're going to learn a rule called the chain rule. Now the chain rule is based on having a composite function. So if y is equal to f of g of x, just like our sine of x squared, the way we find the derivative is we take the derivative of the outside, f, with that g of x inside it, and you leave that g of x alone. And then you multiply it by the derivative of g of x. So you've taken the derivative of the outside, kept that inside left alone, and then multiplied it by the derivative of the inside. So let's look at that function that we just did with sine of x squared. So let's say I have this composite function. We have a function inside a function. And I want to identify x squared. This is inside sine of x. So it could be the equivalent of our g of x. Okay, so the chain rule tells us we're going to take our outside function, sine, and we're going to take its derivative, and we're going to leave alone that inside part for right now. So the derivative of sine is cosine. Now leave alone the x squared. Then we're going to multiply by the derivative of x squared, which is 2x. And I'm going to rearrange so that we avoid the temptation of multiplying x squared and 2x. This is y prime. One more example. So if I have y is equal to the square root of 2x plus 3, this is a composite function. So we could say that our f of x, the outside, is the square root. And our inside is 2x plus 3. And we need to rewrite our exponent. So instead of the square root, we're going to have 2x plus 3 to the 1/2. Now if we look at this as an outside-inside type of application, we're going to start only with caring about that exponent right here. We're going to treat 2x plus 3 just like an x. So if we had an x to the 1/2, how would we find its derivative? Well, we would do the power rule. And that's what we're going to do here. So we're going to apply the power rule to the outside portion, which is that exponent. We're going to leave that inside alone. And when you subtract 1, you get a negative 1/2. But 2x plus 3 has its own derivative. The derivative of that inside is 2. So we can simplify here. 1/2 times 2, that's just 1. And we have 2x plus 3 to the negative 1/2. And our original problem did not have a negative exponent. In fact, it had a square root. So the negative tells me return it to the denominator, and the 1/2 tells me return it to the radical. And this is another example of a chain rule.